in the last class I gave you this problem, x dot is equal to minus, now we will just substitute the value so that you can easily calculate. So, this is the set of equations that we started with, and I asked you to do two things. First, as you have seen, for any dynamical system, if the system equations given, it essentially defines the vector field, and we should first try to get a grip on the character of the vector field. And for that we have understood that the method is that we first locate the equilibrium points, then we locally linearize around the equilibrium points and try to understand the behavior around the equilibrium points first, because these are the sort of pivots in the state space. These are the places where you have good understanding. So, first understand those parts, and then in terms of that, if you can figure out how the behavior is going to be, fine. If it is not possible to figure out, then we will look at the rest of the state space. So, go by that process, because that will give you some understanding. So, first, where are the equilibria of this set of equations? Obviously 0 0 0 is 1, but that is not all, because these guys are there. So, it should give rise to other equilibrium points. Can you find out? Okay. So, one, let us call them A, B and C, 3 equilibrium points. So, the equilibrium points are A 0 0 0, that is obvious. Put 0 0 0, you get the left hand side 0. B is root over okay, root over B into R minus 1. Well, B was this fellow, so, and oh, that is symmetrical. Then have you all got it? Good. And the third equilibrium point, I can see that it should be symmetrical, should be with minuses here, right? This one is also minus, and this one is, have you all got it? Okay, good. The moment we have it, that immediately tells you a few things. First, notice that if R is less than 1, then what happens? Yeah, this fellow gets imaginary, and the position of equilibrium point must be real, because it is in the real state space position. Okay, eigenvalues can be imaginary or complex, whatever, but the position should be real, and therefore these equilibrium points B and C do not exist until R, the parameter, reaches a value of 1. Okay, so that can be inferred immediately. But this fellow is always there. This fellow was always there. So, as you change the parameter, say starting from a value that is less than 1, you are, suppose you are increasing the parameter, then you find that this fellow was there and this fellow was, okay, we will look at the stability later, this fellow was there existing, and at that particular point these two fellows come into existence, earlier they were not there. Can that be inferred? Fine, only that much can be inferred from these equations. In order to infer more, we need to look at the stability of the equilibrium points, and stability of the equilibrium points are obtained from the Jacobian matrices. So, get them, get the Jacobian matrix. So, the Jacobian matrix J at we will obtain it in terms of a general thing, and then we will put the values. So, our this fellow was our sigma and this fellow was our B, right. Let us do it generally, so that you can use other values of sigma and B also later. So, the first term will be minus sigma plus sigma 0. So, it will be minus sigma plus sigma 0. Okay. Second equation with respect to x, minus z plus r, minus z plus r. With respect to y, minus 1. With respect to z, minus x. Similarly here, y, x and minus b. Done. Good. Now, we know that we know these values, we have taken some values here, right. We have kept r as a variable parameter, but for each equilibrium point we can substitute these values x, y and z. Now, if you substitute the values of 0, 0, 0, then what do you get? At 0, 0, 0, you have the matrix, this fellow is minus 10, this fellow is plus 10 and 0, here it is plus r, minus 1, 0, 0, 0 is fine. This would be the matrix, fine. So, can you find out the eigenvalues of this? Just quickly calculate and tell me what are the eigenvalues in terms of r. So, lambda there will be 3 eigenvalues. Has to depend on r. No, it does not depend on r. What are you getting? You want me to do it here? Minus b minus 11 plus minus root 81 plus 40 r whole by 2, and oh, this is plus minus. Okay, is that right? What she says? Where did you go wrong when you said that it does not depend on r? Okay. As I told you, if you have met with an accident, you should be able to calculate the determinant the next day. These are part of your bringing up. fine. Now, let us see what does this tell us. What does this tell us? At r is equal to when is this at r is equal to 1, what is this value? At r is equal to 1 you get -0 and -11, right. So, this one is squareable then 0 and -11. So, there are two eigenvalues, one is widely negative. So, I can comfortably assume that that fellow will remain negative, but another fellow is 0. 0 means exactly at the borderline between stability and instability, right. For r further negative, then what happens? This fellow will be dominating than this part, and therefore, you would expect the no, as yet don't assume that, wait, because there would be some values of r for which this will be real, some values are for which it will not be real, clear. So, find out for which values it will be stable. There are, for r is equal to 1, we have found that it is -11 and 0. So, if you draw the real and imaginary parts, one is here, another is here. As you change the parameter, I can see that either r value is larger or smaller, it should go this way, and therefore, the equilibrium point will become unstable. Okay. So, here is something that is stable eigenvalue, this part is also a stable eigenvalue, and the other part which is now having the value 0 is the suspect case, which can make the system unstable, right. For which value of the parameter does it become unstable? Actually 1, is it not? So, if you probe this question, you will find that below 1, when this there are 3 equilibrium points A, B and C, this fellow was stable. At r is equal to 1, this fellow becomes unstable, and these two fellows come into existence, right. So, you are changing a parameter, one equilibrium point was stable. So, you are happy about its behavior. Start from any initial condition, it will go into that, and at that time all these things were, all the eigenvalues were real, and therefore, it would nicely go into it. At this particular value of r, it becomes unstable. So, what are the eigenvalues then? Do they remain real? No. Try to understand my question. We simply substituted out of my hat r is equal to 1. Why? Because we had some hunch that something happens at r is equal to 1. So, we substituted r is equal to 1 and realized that that is a critical case. So, move it this way or that way, it is going to be unstable, but when it becomes unstable, is it still a real pair of eigenvalues, or is it a complex conjugate pair of eigenvalues here? Still real pair of eigenvalues. Okay, they are still real pair of eigenvalues. Nice. So, you have got the fellow unstable at that point. If you start from that initial condition or somewhere close to it, it will go away. It will go away along. Wait, here is the concept. this is a stable eigenvalue. The other one that was close to -11, that is also stable eigenvalue. There would be eigen directions associated with them, and any initial condition along those eigen directions will not go away. They will come close to the equilibrium point, even though the equilibrium point is unstable. But slight deviation along the unstable eigen direction will grow exponentially, and it will go away along that direction. Okay. So it is just not just unstable any which way, it is unstable in a specific way. In a particular direction it is unstable. Fine. Now let us try to understand the question. If it is unstable along that direction, where does it go? In order to answer that question, you have to find out the stability of these two fellows who have come into existence. If they are stable, so they will ultimately land up there and stay there, right. So find out their stability. For that, all you need to do is to simply substitute these into here. Okay. At this stage, unless you put values, you will find it a little difficult to handle. So put values, these values 10 and 8/3. Calculate. To calculate the stability when, say, the value of r has been pushed to an extent that is greater than 1, say 2. So what will you do? You will say that now my Jacobian matrix is minus sigma minus 10 plus sigma plus 10 0 minus z plus r. Z is r minus 1 and r is now 2, and therefore this is 1. So minus 1, that is z's position, plus r is 2, right. Now here is minus 1 minus x is this, right. Now here it is root over 8/3 into r minus 1 is 1, clear, root over 8/3 here. Now y is similarly x is minus b, fine, is it right? Second line third column minus x. Now you can, these are all numbers, so you can always find the eigenvalues and tell me whether this particular equilibrium point is stable or unstable. Eigenvalues, okay. If you do cubic polynomial, then can you figure out the type of eigenvalues that you are going to get? One thing is to get the values of the eigenvalues. You can always plug it into MATLAB and get it. So I am asking you, can you figure out whether they are going to be real or complex or stable, unstable? That suffices for our purpose. For our purpose, that will suffice. The character of the equilibrium point. I do not really need to know exactly the eigenvalues. I think you will get one real negative eigenvalue and two complex conjugate eigenvalues with negative real part. Check. Have you brought calculators? Without calculators, you are going to have trouble. Oh, that is the problem. You have not brought calculators. Do bring, because we will solve problems as we go and we will often need calculators. Okay. Now let us to cut a long story short. I can see that if I ask you to do it right here, it will take more time than I anticipated. So at these parameter values where I have assumed r is equal to 2, that means I have pushed it beyond the r is equal to 1 level, then these two equilibria are stable, but with a spiral character. Now try to understand what happens. I am just writing the character of the eigenvalues. First eigenvalue is real, negative. Second eigenvalue is the other two are complex conjugate. Can we infer then in the 3D state space the kind of orbits that you are likely to see? Okay, where are they? These two equilibrium points, where is the position? Say B, where is it if you substitute the values? Root over, where is it? Root over 8 by 3 positive. So x coordinate, y coordinate, z coordinate. I will draw in a separate copy. X, y, z. So along the x coordinate you have got something, along the y coordinate you have got something, and along the z coordinate you have got something. So it will be somewhere here. And the other one will be different in the other two directions, but will be okay. Let us put y here and z here, so that the other one can be placed symmetrically. In the z direction, they have the same coordinate. Okay. These two are the equilibrium points. Now, if you have the real eigen value, there should be an eigen vector along which this fellow will be stable. So you can see that suppose you can always calculate that, and I will ask you to calculate that. Suppose this is the eigen direction along which it is stable, eigen vector associated with the real eigenvalue. Okay. There should be also associated a eigen plane associated with the complex conjugate eigenvalues? How to calculate that? Do you know how to calculate the eigen plane associated with the complex conjugate eigenvalues? Not learned. Okay, okay. Then I will have to do that little more. Suppose you have, then let us start from a little backwards, so that we can recapitulate. These are concepts that possibly you need. Here there was a complication that the equilibria are not at the origin. So, let us assume that you have got an equilibrium at the origin here, and suppose this is one stable direction associated with a real eigenvalue, which means that if you have a initial condition here, it will exponentially decay. And suppose there are a pair of complex conjugate eigenvalues, then there should be some kind of a plane associated with it, so that any perturbation along that direction will die down like this, right. Any deviation from this plane will die down because of the action of this stable eigen value, and any deviation along this plane will die down because of the action of the complex conjugate eigen values with negative real part. Fine. So that if you start from any initial condition away from here, it will, how will it behave? It will behave like this, and it will ultimately go towards that. This is a eigen plane in the sense that if you start any initial condition on this plane, it will forever remain on this plane. In that sense, it is eigen plane. How to identify that eigen plane? How to identify that eigen plane? Try to recall the way you solve the problem with a pair of complex conjugate eigenvalues. What did you do? You first, if you write down the characteristic equation, you got in case of a 2-dimensional system a quadratic equation, in case of 3D system a cubic equation, whatever it is, but its solution gave you the complex values. Now, these are eigen values. How did you calculate the eigen vectors? You plugged in these eigen values into the equation a minus lambda I times x is equal to 0. Thereby, you obtain the eigen vectors. Now, these eigen vectors in this case will also turn out to be complex conjugate. So, eigenvalues complex conjugate, if you obtain in the same way blindly, I have these eigenvalues and therefore, I try to obtain the eigenvectors, you will get complex conjugate eigenvectors. Then what was the logic? The logic was that you would say that this complex conjugate eigenvectors were consisting of a real part and an imaginary part like p plus jq, and then you would say that p plus jq is a linear combination of the p and q, and therefore, p and q both are independent solutions, and thereby you would say that any solution can then be constructed out of these two real solutions. That was the essential logic. If you remember those classes in the theory of differential equation, that was how it went. Okay. Do you remember? Silence. Okay. If that condition prevails, so let us solve a problem, simple problem. Let us solve at least one problem, so that we can do this. X dot 2D problem is equal to sigma x minus omega y, and y dot is omega x plus sigma y. All right. From this you will have x dot is equal to a x, where a is sigma minus omega, omega plus sigma. Okay. Then in order to calculate the eigenvalues, you would write a minus lambda I is equal to sigma minus lambda minus omega, omega sigma minus lambda, right. The determinant of this would have to be 0. So, that equation then how to write it? Yes. So, lambda is sigma plus minus j omega. The equations have been written such that you get it essentially. Such that you get it, because I wanted you to handle this form. This is very familiar, right? Sigma plus minus j omega, familiar. So, I assume that you are trading in a familiar domain, and then what would you say? You will have to find out the eigenvectors associated with these eigenvalues. Chalo, I obtain the eigenvectors associated with these eigenvalues. Say a eigenvector is v1 v2. Then you would write minus j omega minus omega omega minus j omega times v1 v2 is equal to equal to 0. So, that will be written as minus j omega v1 minus omega v2, here it is omega v1 minus j omega v2 is equal to, that is what you write. Now, you see they both are the same equations as happens for all eigenvectors equations, but then from here it is possible to identify the eigenvectors. So, what is the eigenvector? From this line can write v1 is equal to j v2, that is the eigenvector equation. Okay. So, it involves j, in that sense it is complex conjugate. Now, how would you identify this? See, we have said that the eigenvector is this vector. These two are related by this. Eigenvector is any vector along that direction. So, it will be very convenient for us to simply say that either v1 or v2 is 1, and then the other, say it will be convenient to say v2 is equal to 1. So, just set v2 is equal to 1. So, v1 is equal to j. So, what do you have? v1 v2 is j, that is the complex conjugate eigenvector. Okay. So, here we started with one eigenvector, one eigenvalue, its conjugate, you take the negative one, it will turn up to be the complex conjugate here. So, we can safely work with this eigenvector associated with eigenvalue this last one. Okay. Then what do we say? How do we proceed? See, when you do that in the 3D, you have to do the same way, exactly the same way. So, only difference is that this will be a 3-dimensional equation, you will get a 3-dimensional thing, but nevertheless ultimately it will lead to the same thing, conceptually the same thing. Okay. So, we have your x t as the solution of the differential equation is the e to the power eigenvalue t times the eigenvector. Okay, that is one solution. Eigenvalue is sigma plus j omega t times the eigenvector which is j 1, that is the solution. All right. So, this is one solution. Now, we can break it into parts, e to the power sigma t and e to the power j omega t, and we know that e to the power j omega t can be written in terms of sines and cosines. So, just do that, then you will get e to the power sigma t times this will be cosine omega t plus j sin omega t times this. So, we will just write it j cos omega t minus sin omega t, and the other one would be 1. So, cos omega t plus j sin omega t. Can you write it like that? Fine. Notice what we have done. We have separated out into two parts, e to the power sigma t times e to the power j omega t. E to the power j omega t we have written as cos omega t plus j sin omega t, and then multiplied with this vector, you got this. Now, we can separate this out into the real part and the imaginary part, can we not? So, we will separate it out, we will get e to the power sigma t times two parts. First part is minus sin omega t cos omega t plus j cos omega t, this one, and sin omega t. So, here we have separated out. Then we say that let this part be called P and let this part be called Q. So, here it is a linear combination of this complex number is nothing but a linear combination of the P part and the Q part, and so we can say that ultimately x t therefore would be, it is possible to write it as C1 e to the power sigma t times this minus sin omega t cos omega t plus C2 e to the power sigma t cos omega t sin omega t. Okay, that was the logic. Fine. Notice that we had complex conjugate eigenvectors, but we went by the same logic that the ultimate solution, one of the possible solution is e to the power eigenvalue t times the eigenvector, but then that allowed us to separate out the real part and the imaginary part, and ultimately we get a real solution. That is the solution of the system. Okay. You understood that? Any question remains? Fine. Now, this is a 2D system, 2-dimensional case. In a 3-dimensional case, all that will happen is the matrix will be a 3-dimensional matrix, 3 by 3 matrix, and you will get a cubic equation. Ultimately, from there you will solve, and a cubic equation may lead to one real eigenvalue and two complex conjugate eigenvalues, or all real eigenvalues. There cannot be any other solution. Now, if you have one real eigenvalue and two complex conjugate eigenvalues, if you have all real eigenvalues, it is very trivial to obtain the eigenvectors. They are all real eigenvectors, but it is not trivial. That is why the concept comes. What happens if you have a complex conjugate pair of eigenvalues and one real? The situation that I have just depicted here. Then how do you obtain this plane? Notice the logic that I was following here. What was the logic? That the real part and the imaginary part individually give two solutions. Okay, have you noticed? Real part and imaginary part of the eigenvector individually give solutions. Real part is a vector in the real space. Imaginary part, that real component of the imaginary part is also a real vector. So you will be able to identify two vectors in this plane, and there can be only one plane passing through these two vectors. So the method is, approach is that if you have a complex conjugate pair of eigenvalues, obtain the eigenvectors and obtain the real and imaginary part separately. The real part will give you one real vector, the imaginary part will give you another real vector. The plane passing through that will be the eigenplane. Okay, have you understood the concept? Often this particular concept is not given in the differential equation classes, but for us, in order to understand what happens in the state space, it is definitely necessary for us to understand these eigen directions and eigenplanes. Clear? Next class I will show you the eigenplanes. From the evolution of a system, you will be able to see, okay, here is the eigenplane, I can see that. But before seeing that, see, doing that by simulation is blind, devoid of concept. You can always, any fool can do a simulation. But what is really necessary is to grasp the understanding that if you have a 3-dimensional system and if you have the one real eigenvalue and two complex conjugate eigenvalues, there must be one real eigendirection and one real eigenplane. Clear? So in the problem that we are originally attacking, that is the problem with this system, then here also there would be a real eigenplane. I do not know where it is, but let me schematically draw like this. Okay, na? Which means that any deviation from here will die down, but any deviation from here will also die down, right? It will be inward spiral. Similarly here, now because the symmetry, we can say that here the directions will be symmetrical to that direction, because all the values are symmetrical. So we will say that here is also another plane like so. Okay. So this fellow was a equilibrium point that was unstable. From here it goes away along that unstable eigen direction, and when it lands somewhere here, it always goes on to these, either this or that. Will it go to here or here? Both are stable. Will it go here or here? You don't know really. You don't know really, right? It might go here, it might go there. There is the fun of nonlinear systems, that there can be two equilibria, both stable, and you do not know which one it will go to. It might go here, it might go there. In fact, it can go to both the equilibrium points. It can go to both the equilibrium points, depending on where the initial condition is. If the initial condition is somewhere here, common sense will tell you that it is most likely go to this one. If the initial condition is somewhere here, it is most likely that it will go somewhere here. but this also tells you that then in the whole state space, if you look at the whole state space, that should be divided into compartments. One compartment, those initial conditions that will ultimately go here, another compartment, those initial conditions that will ultimately go here. Is that right? Fine. So, even though we have not calculated it today, and I ask you to actually calculate the eigen directions, work out that analytically first and then do the simulation. Don't do the simulation first, then you don't develop understanding. But that has at least convinced us that there must be eigen directions, there must be eigen directions like this, and there must be eigen planes like that, and depending on where I start from, the state space is divided into compartments, and that sort of tells, this compartment tells which equilibrium point ultimately I will converge on. Okay. Now, these have certain names. A situation where, I have written a lot, a situation where there are two equilibria and the state space is sort of divided into compartments, so that from this compartment it goes here, from this compartment it goes there. These regions are called the basin of attraction. These regions are called the basins of attraction. So, from this basin, all initial conditions will ultimately home onto this equilibrium point. From this basin, ultimately all initial conditions will home onto that equilibrium point. Now, what is the attraction thing going on here? It is that, see, in gravity you have heard that every body is sort of attracting anything else, and so sun is attracting the earth is attracting the moon, and everything is attracting the others. So, here in this state space you can in similarity visualize these points as sort of gravitating bodies, and anything in this vicinity will be attracted to it. In that sense, these equilibrium points that are stable equilibrium points are also called attractors. So, this would be called then an attractor. So, you might say that the sink type of equilibrium point then is an attractor. A sink is where everything goes, that is an attractor. Well, in linear systems, that is the only type of attractor you have heard of. In a linear system, that is the only type of attractor. These two are that type of attractors. But in the nonlinear systems, you have heard of another type of attractor. What is it? The limit cycle. The limit cycle itself is an attractor. We have discussed that in the last class. The limit cycle is itself in the attractor, in the sense that if you start outside the limit cycle, there is a spiral that goes inwards. If you start inside the limit cycle, there is a spiral that goes outward. Ultimately, it homes onto that. In that sense, the limit cycle is also an attractor. Okay. So, linear systems theory will tell you that there is only one type of attractor, the point attractor. Nonlinear systems theory will tell you that there is also another type of attractor, the periodic attractor, the one that goes on. And all oscillators, as I told you, are attractors like that. They are also attractors. In the state space, you can see them as attractors. Now, from the stable equilibrium point, how does the limit cycle kind of behavior develop? That I have already covered. When the eigenvalues here, were earlier complex and negative real part, if with a change of a parameter, think, if the eigenvalue here were complex with negative real part, so that the behavior would be incoming spiral kind, and with a change of the parameter, if they move like this, so that at a certain parameter value they become outward spiral because of the nonlinear behavior of the system. This behavior that I was talking about, the outgoing spiral behavior, that pertains to only a very close neighborhood of that equilibrium point, elsewhere it may still incoming, thereby the limit cycle develops. So, what is actually happening at the equilibrium point if I calculate the eigenvalues? It is this. Eigenvalues that were real, that was complex with negative real part, were moving this way, so that the real part becomes positive. That is what happens. For our system, the 3-dimensional system that I have given, does something like that happen? Try to find out. Does something like that happen? These equilibrium points, you can find the eigenvalues. So, I will ask you to work out, do these eigenvalues for some parameter value do something like this. If that happens, then I would expect after some time these behaviors to develop. Okay. No. These kind of behaviors to develop. All right. So, that can be worked out from the from looking at the local linear neighborhoods. Do that before coming to the next class. So, at which parameter value does this happen? Beyond that, still see, these two are separate. These two equilibria are separate, and they have each their own basis of attraction. And beyond that, if you change the parameter, what happens? That you will not be able to infer from linear systems theory. So, the linear systems theory will tell you that something that you are comfortable with, will tell you what happens near the equilibrium point, and you will be able to infer the occurrence of limit cycles. Come to this extent before coming to the next class. Okay. I still don't want you to do the simulation, that you will do later. Try to do things as much as possible by analysis. Okay. That is all for today.